So I am going to talk today about cybercrime prevention and linguistics and computer science. It's an interdisciplinary project that took place roughly between 2016 and 2023. And it was carried out at the University of California, Davis, in the US. Let me see. So yeah, so this is going to be the structure of the talk. First, talk a little bit about cybercrime and cybersecurity in general. I will present the new interdisciplinary approach that was actually motivated by an initiative from the National Science Foundation. I will lay out the research program that our team developed here at UC Davis and the application we developed. We called it Tronto for Trustworthy Ontology. The application used lots of data sources and also technologies from the semantic web. From there, then I will move to talk about the key results and discoveries from the can you still see my screen?
Yes.
Yeah, okay. Key results from the research, and then I will close with some lessons and reflections. And so, as I said before, to me, the most important thing, besides presenting some results, is to talk about the place this research had in my own career, my own development as a linguist. Okay, and I will try to leave plenty of time for questions and discussion. So cybercrime and cybersecurity, as we said, it's now all over the place. We're constantly, assaulted by phishing scams, and cybercrime takes different forms: online bullying, online fraud, denial of service attacks, ransomware, as I was saying, in this town in the South San Francisco Bay, identity theft, data theft, hacking, even piracy, and there's more, right? These are some of the variety of cybercrime that we know exists. Researchers have divided them into two major classes. Type 1 cyber attacks usually are singular events that involve some form of malware, and they exploit system vulnerabilities. Denial of service is one of those, for instance, or ransomware, right? But there's also type 2 attacks. They tend to involve multiple events, no specialized programs. And an example could be cyber stalking, somebody who follows, keeps posting messages on your Facebook feed, or tries to send you annoying text messages, things like that, right? The interesting thing about these type 1 versus type 2 division is that there's a mix of the two categories sometimes. Some attacks may involve a little bit of each, which brings us to the next topic, which is that cybercrime and cybersecurity is not just a technological issue, it's not like a social issue, but a combination of the two. So this is why, in order to address cybersecurity, we need a interdisciplinary approach that combines both social sciences and the technological side in the form of computer science or information science, right? The typical standards for this kind of approach involve what they call the CIA standard, which is confidentiality, integrity, and availability. And this addresses the data side of the equation. So yeah. So what was the new interdisciplinary approach? Two directorates, the computer and information systems and the social and behavioral economic science directorates from the National Science Foundation decided to come together and say, well, since cybersecurity is this complex problem that requires interdisciplinary solutions, let's launch it. We don't have any interdisciplinary teams that are really active. So what they did is they launched this small initiative, these sort of the seed grant for groups to come together and address some aspect of the problem, right? So the two ideas that we came up with were to address the question of automated methods to train or nudge end users to improve cybersecurity posture, and also investigate the impact of trust and institutional design on cybersecurity decisions. We got 2 grants, an eager, which is a smaller seed grant, and then later on a bigger grant to develop this ontology for cybersecurity. And our team consisted of myself as the PI, my colleague Kenji Sagae from linguistics, who is computational linguist, and then 3 colleagues from computer science, Prem Devanbu, Vladimir Filkov, and Matt Bishop, who was who had higher expertise on cybersecurity. Devanbu and Filkov were more on the programming languages and language modeling side of the equation. What was our research program? The starting point was our observation that the web holds vast and structured and semi-structured information about cybersecurity. There's a lot of chat and conversation and questions and answers about cybersecurity over there. We wanted to use that amount of language to sort of to help automate the way in which people find this information. All right. So for that, we plan to leverage semantic web technologies, which meant building an ontology that is a way of representing knowledge. So we wanted to represent the knowledge that online discussions about cybersecurity were that was contained there in an automatic form that could be reasoned over and also interrogated by users. Okay. The methods were to build language models that would then extract that knowledge, populate an ontology, and then find ways to provide the users with up-to-the-minute feedback on emerging threats and patches and things like that. To give you an example, this was the famous Heartbleed virus that was circulating on the web around 2016 or so. And this is the kind of conversations that we were using. You could see this, let's say, in StackOverflow. Question: I am using HTTPS and TCP over SSL in a Java application with key stores and trust stores. I use self-signed certificates. I came to know about Heartbleed vulnerability with OpenSSL. Do I need to change any implementation from the Java side? Answer: Java does not use OpenSSL, although some Java applications like Tomcat can. As you are using key stores and trust stores, you must be using Jessie rather than OpenSSL. So there's a question about a program that uses a library. Is the library infected by the virus or not? And the answer is starting to give some information, but there's a lot of additional inferences that the user must take. So we could represent this knowledge and the inferences in an ontology, which is you see in the diagram on the right. So libraries will be infected or healthy, but that's something we can conclude by looking at a particular virus and see that it will infect a library only if that library is written in C, not if it is written in Java. And because the user is not using one of those libraries in their application, the conclusion should be that the application is safe. So we wanted to do something so that giving this ontology that we extracted automatically from the conversation on the online forum, then we could give this information directly to the user without users having to go through searching or waiting for answers online. For that, we built a target application that integrated the vulnerability information, did some ontology-based reasoning, then queried some up-to-date social media, provided severity summaries, and in this way, the users needed no specialized domain knowledge. This will be the structure of the application. You can see that the second column gives you the data streams, the common vulnerabilities enumeration, which I will talk about in a second, Twitter, other chatter, like the one we set from StackOverflow, and an ontological representation. And then you have two streams from that. One that builds the ontology and uses also the semi-structured information, the CVE side, and then a reasoner that reports on the status of the system that the user is concerned about. And that will leave us to two separate problems that we face, and we try to find technical solutions to. Let me see. Maybe I can take a little second to see if there's any questions. Anything that I may need to clarify. No? And everybody can still see my screen, okay? Okay. All right. The data sources we use are posts from Stack Overflow, Stack Exchange, Reddit, and Twitter. For testing and training purposes, we built parallel sets of posts related to security and posts that were unrelated, so that we make sure that the data we are gathering and the models we were building were really about security, and the signal was a clear signal. All right. Now, on the other hand, we also use these structured repositories, which have all these acronyms. It's really hard to navigate some of them. The most important one is the NVD, the National Vulnerabilities Database. That's a database that collects and organizes all the current information about the known vulnerabilities. And it uses elements from the common vulnerabilities and exposures, which is a listing of all the vulnerabilities, and the common weakness enumeration, which is a classification of vulnerabilities. It took me a long time to navigate this and understand what all these acronyms were. But it was very useful to use. And let me see if I can give you a sense of what is a CVE entry would be for the heartbleed virus. Let's see if this works. So let me change my sharing of the screen. So I hope you can see that now. Yes? All right. So this is an entry for the heartbleed virus. So it gives you a description. It gives you metrics saying that the risk is high, that 7.5 is high risk. Some other information in the form of vectors of analysis. So all of this is entered by some human analyst that is looking at this vulnerability. But also there's all these links to other URLs and other advisories and other discussion. All that was accessed by our system, which provided a huge corpus of descriptions and language about this particular vulnerability, okay? So all of these websites went into our modeling of each of these vulnerabilities. So there was a lot of conversation about this. There's some more information at the bottom. So you also have a classification. We're using the weakness enumeration. So it is an out of bounds read. It's a particular type of cyber attack and exploiting a particular vulnerability, right? And also you have a list of all the software and hardware that can be affected by this virus. These are all the configurations. There's a lot of information to process. You really have to be an expert to be able to read through this entry and know if it's going to affect your own system, right? So we wanted to automate this, that somebody could check in, just enter the name of their system regularly, and our Toronto application would tell them if the system was still secure or it had been some new emerging threat that they should be concerned about, right? And so the linguistic side of this was that we were sort of, you know, where there's language, there's linguistics. So we were looking at the ways in which our knowledge of how to model these kind of linguistic information could be then poured into the ontology and then served to the user in ways that they could act on it, right? All right, let me see if now I come back to the PowerPoint. And again, if there's any questions or anything you want me to clarify, I'm okay with that. All right, so these were the linguistic sources that we use in our modeling, and these are some of our key results. One of the problems we identified that really scared the hell out of us was what we call at that time the problem of insecure dependencies. If you're running any piece of software, let's say, even if you open an Adobe PDF on your computer, that PDF is not unsafe by itself. It is unsafe because it depends on or is using some other library or program or sort of basic piece of software that is vulnerable or that has, or somebody has discovered a vulnerability of that library. These are called dependencies. So you know, software developers don't develop the entire system. If there's something that's going to handle, let's say, traffic in and out of a web page that's already built, they will integrate it into their specific application, and it makes their life easier, right? If that library that program depends on is compromised by an exploit or by a vulnerability or an attack, then the program is vulnerable. But you wouldn't know unless you know the dependency. The problem is that programs and programmers do not need to disclose all the dependencies in their own application. So we were trying it, and if you go back to that dialogue about the Heartbleed virus, you see how that worked, right? The developer was asking, is my program safe? Is my application safe? And the answer was like, well, it depends on which libraries you're using. If you're using a library written in C, it is unsafe. If you're using an application written in Java, you're fine. But how are we going to know? We had to look for every single application in the universe, what their dependencies are. And that was nowhere to be found. We couldn't find it. All we could do is infer it from some kind of, you know, bulletin or conversation or something that people had said on the net. And that was really scary because we couldn't know for most applications if they were safe or unsafe. This was addressed at some point in the US by what some experts call the software bill of materials, which is like a recipe. I'm sorry, it's like a label. You know, when you buy something in the supermarket and you have a label with the ingredients. Some genius had the idea that we should require all applications that they have this list of ingredients, that they list all their dependencies so that we know whether they are secure or not. And in fact, this was later turned into an executive order. At the time, we were wrapping up our research, actually, by President Biden. That's Executive Order for 14028, which mandates bill of materials compliance. And I checked, last I checked, President Trump has not gotten rid of that executive order. So that still stands. The problem is that that developers are not complying with it because it's just too much work and nobody's policing it. So we're still in the Wild West in that respect. So we had a hard time dealing with that. Now, the other result was trying to integrate Twitter in the stream that we were reporting on. And we had some success. Besides dependencies, another factor that we had in our ontology was severity level. You cannot patch every vulnerability in your system, so you have to prioritize. That's why the NVD gives us a sort of a security score. So if something is above 7, you want to do it right away. Something's below 7, you can wait until you have time. The question is, how do you know if something is risky or lower risk? Well, it takes a human analyst to do that. We wanted to see if there were linguistic signals in the documents that describe or discuss the vulnerabilities that would reveal the risk. That means if you have a lot of programmers or developers talking on Twitter saying, we need to do something about this right away, you don't need an analyst to tell you whether that is risky or not. You know that people are freaking out online. That's risky. Let's take care of it, right? So that was the idea. Use the sentiment that was reflected in online chatter to anticipate the security risk level of emerging threats. And there was a group that was already trying to do that using just, run-of-the-mill sentiment analysis of Twitter, which is something that NLP people do. That's the red line in that graph. And the more tweets you consider, the results were worse. That means there were a few people who were actually very good at predicting this. But when you start to look at the majority of the tweets, people are like, well, I don't know, this may be risky, this may not be risky. What we did is we trained our system on the NVD materials right away, and we got slightly better results, more reliable results, right? So anyway, I could talk more about this, but that was a nice result of our system. Let's see. All right, some lessons. For me, this was an important moment. I learned a lot about doing language modeling, which is something I didn't know about, right? Coming into this research, I was talking about language in terms of syntactic trees. My colleagues in computer science were like, no, we don't want that. We don't need that. We talk about entropy and, surprisal and curves, probability curves. So they were already doing this kind of probabilistic modeling based on corpora. And it was very interesting to me to learn about that and compare that to my approach. So the first thing we found was that disciplines have their own vocabulary, our own standards, our own methods. And you need to start talking to people who don't work like you. That's a challenge. We managed to do that. The other problem is that there is no interdisciplinary yardstick. Nobody can tell you whether your interdisciplinary publications adhere to the standard of either of the disciplines that are being, cross-pollinated in this research. We had a hard time finding places to publish our research because, it's neither linguistics nor computer science, it's something else. And as I said, the example of language model versus structural analysis was one that was interesting to me. What I'm giving you here is a quote from an interesting article by Frederick Jelinek. Jelinek is one of the founders of language modeling, of the statistical approach to language modeling that we're now familiar with. Research started at IBM. He's famous for having said, whenever I fire a linguist, our system performance improves. Then he said, well, I don't remember saying that, but apparently people say I did say that. So let me revise this statement and give you the history of our project. The interesting thing he says is that, and I put that in bold, our endeavors were guided by strict scientific principles. So they gave us 2 linguists who were going to guide our progress, right? And they said, we need to build a model of this language. Oh, we'll just write a little grammar. That's what the linguist said. And he says, after a while, the linguists got frustrated. They left our group and returned to their basic research. And this is what he thinks that people think he said when he said, every time he fires a linguist, the system improves. So the thing is, and I found this myself, that at some point I was doing something and didn't want to keep doing. So my involvement with this project was very interesting. It really gives us support, it advanced knowledge, it helped me understand what language modeling is. We were using, technology moves really fast. We started doing a sort of, run-of-the-mill n-gram statistical modeling of our language. Then we moved on to using BERT and sort of using pre-trained neural models. And every week, my colleague Kenji Sagae would come to our meeting and say, no, scratch that. There's a new language model that is, 10 times more powerful. We need to retrain everything using that, or we're going to get better results. And I was like, what's going on? I don't even have time to understand the language model that happened like last week. And now there's a new coming up. What's going to happen next week? Do I need to invest time in keeping up with this technology that changes more rapidly than I can understand? And in the end, all I want to do is go back to talking about, 19th century discussions about South American grammars. That's what I want to be doing. So at some point, what I did is I took Jelinek's advice and I fired myself. I said, if I leave this program, I am sure that the performance of the system will improve. So that's when I had to say, well, I am not going to pursue this kind of research further. I'm going to go back to my basic research, right? So I had arrived at this kind of research via quantitative corpus analysis. But what I got out of it was I learned a lot about semantic web technologies and using those technologies to do modeling of language in the form of ontologies. And that's something I kept pursuing because that resonated better with my earlier research programs. And I have a publication about that. I also got interested in the matter of how we deal with technological and scientific language. And this is something that linguists have been worried about for a long time as well. Even Leonard Bloomfield was concerned about this. He was concerned about the language of science, what people thought about this language of science and technology, this particular jargon that develops, and people start to think that, well, this may be individual separate languages. You could apply the same to programming languages, whether programming languages are written as technical languages for machines to understand, or whether we are writing them for ourselves as developers to be able to understand and formalize the algorithms and other processes, right? So this kind of concern with these technical languages is something that also engages my imagination and my interest as a linguist. All right. So several publications came out of this. They address some interesting aspects, and they keep getting citations, even though the members of our team are no longer actively engaged in this kind of research. And that's it. And thank you. And there's plenty of time for questions and discussion, I think.